We are so close, my friends. This is the second to last content lecture, and we're talking about problem solving and reasoning. So let's jump into it. This is what we'll be covering today. So I'm going to go through problem solving, starting with sort of the basics and then getting to insight. We'll look at fixation, and then we'll move on to talk about analogies, deductive reasoning, inductive reasoning, and heuristics. Let's start with problem solving and insight. We've already talked about Gestalt psychology in terms of sensation and perception. So, Gestalt is a German word meaning form or configuration, and they take the approach that the whole is different than the sum of its parts. In terms of perception, the experience that they're talking about is when you have that sudden change that's called a Gestalt switch. So, when you go from seeing the two faces to the vase, that's a Gestalt switch. And Gestalt psychologists were really just interested in a number of areas of psychology, including learning and memory, problem solving, attitudes, and beliefs, where you could see this theme, this idea that the whole is different than the sum of its parts. So the Gestalt theory of problem solving revolves around flashes of insight. Insight is the sudden realization of a problem solution. And in problem solving, this involves building a schema in which all of the parts of the problem sort of fit together. Insight is a sudden reorganization of information so that the schema solves or fits the problem. And insight can be the result of removing mental barriers or finding an analogy or restating a problem's assumptions or a problem's goals in new ways that make the problem easier to solve. But essentially, you're figuring out a new way to think about the entire structure of the problem. And restructuring is the process of changing a problem's representation. You're probably having a similar experience with this image. You have an initial interpretation, but there's something not quite right about it. So you need to rethink your original interpretation, and restructuring can lead to a sudden insight into what you're actually seeing or what a problem is really asking. So remember that Gestalt psychologists were obsessed with the whole. A problem is only a problem because it's incomplete. The solution makes it complete, and finding the solution closes that incompleteness. Closure is accompanied by a flash of insight or an aha experience. And the aha experience is when you find another way of representing a problem and its solution. Let's look at an example. So, swimming under a bridge came two ducks in front of two ducks behind two ducks, and two ducks in the middle. How many ducks were there in all? Probably this is what you imagined. The description makes you think of pairs of ducks, but suppose you're told that they were swimming single file. Now you might realize there's another organization that fits the description, and the answer to that one is that four ducks organized like this is what you might be seeing. So during insight, problem solvers figure out a way of representing a problem that enables a solution. When you realize that four ducks is a simpler solution to the problem, you may have experienced a sort of Gestalt switch that is characteristic of insight problems, that aha moment. A stranger approached a museum curator and offered him an ancient bronze coin. The coin had an authentic appearance and was marked with the date 544 BC. The curator happily made acquisitions from suspicious sources before, but this time he promptly called the police and had the stranger arrested. Why? This is an example of an insight problem. One of the questions that comes up in this area of research is insight real or is it epiphenomenal? Does it indicate that you've actually reached a solution, or is it just indicative of a new way of looking at things? Maybe like a restructuring, even if that restructuring is not particularly successful. By the way, the reason why this is suspicious is because the designation of BC, you wouldn't know it at the time. That designation was invented literally hundreds of years later. So evidence around whether or not that aha experience, that aha moment is real or whether it's epiphenomenal, evidence actually points to the idea that it actually is real. It's indicative of something. So Metcalf and Weave set out to find evidence for the existence of insight, that flash of insight, and evidence that that experience was real. And they had participants either solve algebra problems or solve insight problems. So what they had participants do is, if the answer actually appeared suddenly during insight problems, you should be able to see that participants have no awareness that they're near the solution. Compared to algebra, they should have some awareness. And so to gauge their experience, the researchers had participants in both groups report warmth judgments every 15 seconds. And their warmth judgment was to indicate how close they thought they were to solving the problem. All right, so here are the results. Participants solving algebra problems reported a linear increase in warmth as they approached the solution. But participants solving insight problems actually had only an inkling of the solution just before, maybe 30 seconds before they reported the answer, suggesting that this feeling of insight, this flash, the fact that it's sudden is real. That is literally how it works. It's a sudden reorganization of the information. But there's still the question about whether or not it's indicative of a solution. So another set of researchers looked at this by having participants watch magic tricks, videos of magic tricks. And then they got to repeat that. Then participants were asked to press a button if they thought they had solved how the magic trick worked. They would then give a global rating followed by how did you have an aha moment, and like how big was that aha moment. So that's like a slider where it's not just a yes or no, it's sort of a relative judgment. They then asked them 4 other ratings. So the solution came to you suddenly, the solution, they had to describe the solution so that the researchers could tell if they were accurate or not. How certain were you that it was correct? And then they would judge whether or not that solution was actually correct. They divided the participants actually based on whether or not the solution was correct, and looked first at the aha rating. So first of all, you can see that people have the aha experience even if they're having an incorrect solution. However, you can see that the aha rating is qualitatively different when participants are correct. So the stronger your aha experience, the more likely it is to be correct. They also looked at the solution time as a function of the correct versus incorrect, and as a function of the aha rating. And again, so you can see immediately that correct solutions have a stronger aha rating, but that also they tend to have a faster solution time. So these results cast doubt on the assumption that the occurrence of the aha experience serves as a definitive signal that a true insight has taken place. But it's probably indicative that there are qualitative differences of the aha experience based on whether a solution is correct or not. So I think the strength of the aha experience is probably more indicative than the experience of aha generally. I think aha is getting at a restructuring, whether it leads you to the solution or not. So Graham Wallas was a social psychologist interested in creativity, and in 1962, Wallas proposed that insight, or this moment of illumination, was a process with 4 stages. He talked about preparation, where the problem solver gathers information about the problem, and this is characterized by periods of effortful, often frustrating work on the problem with very little progress. Then you have my favorite stage, incubation. During this stage, the problem solver sets the problem aside and seems not to be working on the problem. And Wallas argued that the problem solver actually continues to work on the problem during this stage, but does so unconsciously or without conscious awareness. This period leads to the 3rd stage, illumination, in which some key insight or new idea emerges, paving the way for the 4th insight, verification, in which the person confirms that the new idea really does lead to a problem solution and works out the specific details. This to me actually really sounds very familiar. I've had that experience where I have been trying to solve a problem and there's just this sudden like, oh, I have an idea. And you know what? Sometimes it doesn't lead to the solution, but it's sort of an exciting time where it feels like the next step is verification. And like most of the time, that sudden restructuring does lead you to the solution, at least, or a more effective approach. Um, so there's also some historical evidence in favor of these stages. Watson and Crick's discovery of the double helix is often cited as an example. But in reality, it was actually probably a series of mini insights that led to the final description. But this idea of insights still following a period of incubation is actually very interesting. Anecdotally, people often report this kind of experience, right? So you're trying to figure out a problem, or how to solve a problem, and you get really frustrated, you set it aside, you're doing something completely different, and suddenly the answer just comes to you, right? So incubation seems to be doing something. Is it real? Is incubation really helpful? Well, there's actually some interesting evidence on this. The findings are kind of mixed. They're not totally consistent, but at least some experiments suggest that setting aside the problem will help. So, in this research, participants were presented with an insight problem similar to this one. This is an insight problem which actually seems to imply that this is an algebra or a geometry problem, but in fact, this is a logic problem. So, if the length of the circle's radius is r, what's the length of x? The length of x is r, because literally x and r are exactly equal. You just have to draw that diagonal in order to see that explicitly. So if you realize that the diagonal is the radius of the circle and that both diagonals are a rectangle of the rectangle are the same length, you can just really already jump to that conclusion. So it was actually a harder problem than this that the researchers used, but similar in its solution, that it implied that it was sort of a geometry or math problem, but in fact the solution could be got at a little bit more directly. And then they had participants set it aside for some period of time. During the break, participants were in one of two conditions: either a demanding task where during the break they did crossword puzzles, or they were in the break doing a non-demanding task where they were just actually asked to leaf through newspapers and magazines. They also manipulated the duration of the break, but that seemed to matter less. So let's look at the results here. So if we look at the y-axis, is the proportion of solutions as a function of no break. So comparing, that's a good control condition. Short break versus long break. And you can see that having a break matters, but the length of the break actually doesn't seem to really make a huge difference. So having a break, setting the problem aside, helps people reach a higher number of solutions. And interestingly, if you're doing a demanding task during the break, you're more likely to reach the solution compared to if you're just doing something relatively mindless or non-demanding. So at least some experiments suggest that setting aside the problem will help. And this maybe implies that the way that incubation helps is potentially allowing you to think in new ways or experience new content. And these are, in fact, some of the explanations. So why do breaks help? Well, one explanation is, and probably I think the most interesting explanation is unconstrained spreading activation. So when you're actively trying to solve a problem, you are potentially activating pathways that are actually not helpful because you are directing the flow of information consciously. And so you might be working off in one direction, not getting to a solution. When you incubate, when you set this problem aside, now that activation can kind of go wherever it wants, including spaces that might be more effective for leading to a solution. So by setting it aside, you let your unconscious activation spread wherever it might be. This is probably the explanation. Number two, encountering new information is probably closer to what might be used to explain the last set of results, because working on demanding tasks seemed to help. When sorry. So yeah, interruption may allow you to gather new information. So you might just stumble across some cue in your environment, um, or in your memory that tells you how to think about this problem, and you come to a solution. In other cases, your early efforts with a problem might be tiring or frustrating, and just interrupting that provides an opportunity for your frustration or fatigue to just dissipate. And then finally, release from fixation. If you put the problem aside for a while, it's possible you'll forget about earlier tactics that were not effective, freeing you to explore other more productive avenues. So essentially, releasing you from fixation. Which brings us to fixation. So here's a really interesting problem from the problem solving literature. Suppose you're a doctor faced with a patient who has a malignant tumor in his stomach. It's possible to operate on the patient, but unless the tumor is destroyed, the patient will die. There's a kind of ray that can be used to destroy the tumor. If the ray reaches the tumor at sufficiently high intensity, the tumor will be destroyed. Unfortunately, at this intensity, the healthy tissue that the ray passes through on the way to the tumor will also be destroyed. At lower intensities, the ray is harmless to healthy tissue, but it will not affect the tumor either. What type of procedure might be used to destroy the tumor and at the same time avoid destroying healthy tissue? To solve this problem, you have to switch from viewing the problem involving a single ray to a solution involving dividing the ray into smaller rays. Let's look at another problem. Suppose you have 8 coins in a balance. One of the coins is counterfeit and therefore lighter than the others. How can you find the counterfeit coin by using the balance only twice? Most people initially think of dividing the coins into 2 groups of 4. One group will be lighter, so that's the group with a counterfeit. Then you divide those 4 coins into 2 and 2, weigh them against each other, but now you've only narrowed it down to 2 coins. That doesn't reach the solution. The problem that people face when they are trying to solve this is that they fixate on initially dividing the coins into 2 piles, and that will never lead to the right answer. So the solution is that you have to divide them into a pile of 3, 3, and then another pile of 2. You're then going to weigh the 3 versus 3 against each other, and they should be equal. If they're equal, then it's one of the other 2 that is left over, and you can just weigh those 2 against each other and figure out which one's counterfeit. If it turns out that the counterfeit is in one of the 2 piles of 3 so that they are unequally weighted, then all you have to do is take the lighter pile, weigh the 2 against each other. If they're equal, then it's the leftover one. If they're not equal, then the lighter one is the counterfeit. So here is another problem, the candle problem that we've talked about before. You're in a room with a cork board, candles, matches, and a box of tacks. And the goal is to mount the candle on the cork board so that it will burn without dripping wax onto the floor. So fixation and all of these problems help to illustrate this idea of fixation. So fixation refers to a person's tendency to focus on specific characteristics of the problem that keep them from arriving at a particular solution. Here, people fixate on the idea that the matchbox is the tack box is only used to hold the tacks, when in fact it also can be used as a candle holder. In the original research of this problem, Dunkirk found that participants were significantly impeded if the matches or the tacks were presented inside the box compared to when they were presented the box empty with the tacks outside of the box. They were priming the box for its traditional function, and that really would prevent people from thinking about using that box in a different way. Often fixation is the result of a familiarity with a situation, or in the case of functional fixedness, it's familiarity with the function of a particular object. Functional fixation refers to the effect that occurs when the idea a person has about an object's function inhibits the person's ability to use the object for a different function. It turns out that a coffee pot cannot just be used to make coffee, it can also be used to make some pretty mediocre couscous, probably. I wouldn't eat it. I would doubt it's food safe. Here's another demonstration of functional fixedness in adults. So this is the two-string problem. The goal is to tie together the two strings. And 60% of people can't solve this problem initially. But when the experimenter accidentally brushed against one of the strings and set them into motion, about 62% of participants would solve the problem within 60 seconds. The swinging of the string triggered a restructuring of the problem that released them from the functional fixedness and helped them realize that the pliers could be used as a weight in order to produce a pendulum. You swing one of the strings, you hold it, you wait for it to come back, you tie them together. Some developmental psychologists have found a really interesting exception. So, if you look at functional fixedness in 5, 6, and 7-year-olds, you get a very strange pattern of results. In this experiment, participants were divided into their different age groups, but all of the participants faced a task in which they had to figure out that a box could be used as something to stand on and not just as a container. In the pre-utilization condition, the box was full of items, demonstrating its convention as a container. In the no pre-utilization condition, the box was presented to the children empty. So if we look at the amount of time it takes to get to a solution, you can see, first of all, if we look at the no pre-utilization, participants are coming to an answer fairly quickly, and as they grow older, they are faster. So that makes sense. Like more cognitively developed, they're going to execute cognitive tasks faster, right? Look at that though. So you can see the 5-year-olds are not bothered by the pre-utilization. They see immediately that that box, even though it has something in it, could be used in another way. 6 and 7-year-olds clearly feel differently about that. So why was functional fixedness not present in 5-year-olds? Well, it turns out that around 6 years of age, children start to assume that the function of an object is what it is designed for. But children who are younger than 6 often assume that the function of an object is dictated by the goals of the user. It actually becomes this weird rule that kids adopt around 6 years of age where they're like, oh, I see how the world works and these are the rules. One of the rules is objects have particular functions and you have to use them for particular functions. It's actually a really what's the word? Functional adaptation. Like it literally is a cognitive adaptation because it helps kids acquire categories more effectively. It helps them like work out what objects are to be used for, but at the same time it makes them become incredibly fixated on functionality and really subject to functional fixedness at a strong level that kids under the age of 6 are not subject to. And this just really starts to like feed into that idea that like as kids grow older, they start to create categories and they start to use those categories in order to try to understand their world. They actively are using those categories to understand their world. This is one of my favorites because I am the type of person who does this sort of thing all the time. So a mental set refers to the tendency to respond inflexibly in a problem situation, even though a better, easier solution is to be had. So, for example, in this experiment, researchers asked participants to solve these problems, giving them jug A, B, and C different quantities, and then the desired quantity at the end. All 8 of these problems could be solved using this basic formula of B minus A minus 2C. But if you look at the last two problems, even though this formula works, there is a faster, more direct solution. So for question 7, if the desired outcome is 18 units, all you need to do is add jug A and C together in order to get that 18 units. For question 8, to get to 25 units, all you need to do is take jug A and minus jug C in order to get to 25 units. But who follows that shorter route? Well, it turns out it depends on which direction you start these problems in. So if you start with problems 1 through 6 and then you get people to 7 and 8, you can see that the percentage of participants using the shorter solution is like 25%. It's like a quarter of people. 75% of people are doing it the long way. However, if you start people at problem 7 and 8, they immediately go to the shorter solutions, showing that it's actually the iteration of using this approach to a solution that actually just is getting reused over and over again, even though there's something a little more effective that's out there. And here is one of my favorite examples of mental set in action. She's trying to put her shoe through this hole. Her shoe does not fit when it's on her foot. She doesn't need to put her shoe there. She could just put her foot there. I love it. Okay, I forgot last week to put these in, but I'm remembering this week. This is the point at which you could stop and go do problem solving, restructuring, incubation, and fixation. All right, let's talk about analogies. Start with a story. A small country was ruled from a strong fortress by a dictator. The fortress was situated in the middle of the country, surrounded by farms and villages. Many roads led to the fortress throughout the countryside. A rebel general vowed to capture the fortress. The general knew that an attack by his entire army would capture the fortress. He gathered his army at the head of one of the roads, ready to launch a full-scale direct attack. However, the general then learned that the dictator had planted mines on each of the roads. The mines were set so that the small bodies of men could pass over them safely, since the dictator needed to move his troops and workers to and from the fortress. However, any large force would detonate the mines. Not only would this blow up the road, but it would also destroy many neighboring villages. It therefore seemed impossible to capture the fortress. However, the general devised a simple plan. He divided his army into small groups and dispatched each group to the head of a different road. When all was ready, he gave the signal and each group marched down a different road. Each group continued down its road to the fortress so that the entire army arrived together at the fortress at the same time. In this way, the general captured the fortress and overthrew the dictator. Yay! Does this story sound familiar? Any part of it? Maybe not the superficial features, but how about the structural features? This is where we get into analogical problem solving. And I love this quote precisely because it contradicts itself. A good analogy is like a diagonal frog. The point that Kai Krause is trying to make here is that a good analogy doesn't exist. Like the idea is nonsensical. But the fact that this analogy is so good at communicating that makes it a contradiction in terms. So, analogies involve making a comparison to show a similarity between two different things. It puts two situations into some kind of alignment so that the similarities and the differences can really become more apparent. And I love analogies. So, analogic transfer is the application of the problem solving strategies experienced in solving one problem to the solution of another similar problem. We talk about it in this area of research. We talk about the source problem and the target problem. So, the source problem is going to be the first problem that is presented plus the solution. And the idea is, what are the features that make it easier or harder for people to take that source problem and apply it to a target problem? And usually there's going to be some shared similarities, but that's sort of what researchers are often manipulating is how similar and what features are shared. So from the beginning of this lecture, I talked about the radiation problem, and this is the idea of destroying the tumor without damaging the tissue that it passed through. And the radiation problem is solved by bombarding the tumor in the center with a number of low intensity rays from different directions. FYI, this is literally how radiation for cancer treatment works. Is they triangulate it so that the radiation is most intense and centered right over the location of the tumor. So this problem fits with the Gestalt idea of representation and restructuring. The initial presentation of the problem involves a single ray, but the restructured solution involves dividing that ray up. All right, so let's look at how good or bad people are at analogical transfer. So we're looking here at the percent of people who actually solve the problem, and we're comparing no source problem at all with a source story present, and then a source story with the hint of using the source story to think about the current problem. So if you give them a source story like the fortress problem, only about 10% are going to solve it spontaneously. If you give them a source problem like the fortress story, but you don't hint that it's related to the target problem, you're still going to get like about 30% of people who transfer, but that's still not a tremendous amount. But when participants are told to think about the story that they had read, it jumps up to about 75% of participants who arrive at the solution. There's no new information across these two conditions of having the source story versus thinking about the source story. The only difference is perspective and attention, essentially. Noticing is highly influenced by surface features. So surface features are the specific elements that make up a problem. I have here this idea of like a computer mouse and animal mouse because superficially those things are similar to each other, but like that's literally surface features alone. Functionally, structurally, they are different. And this gets at structural features. So structural features are the underlying principles that govern the solution. So rays and tumors, that's one kind of set of surface features. And you can compare that to roads and the armies, right? It turns out if you make the surface features more similar, people are better at using them in order to solve an analogous problem. Structural similarity means that the relationship between elements of the problem in the source and target problem are the same and independent of the similarity between the surface features of themselves. So it's actually the relation that governs the solution. All right, let's look at another story here. A small country was controlled by a dictator. The dictator ruled the country from a strong fortress. The fortress was situated in the middle of the country, surrounded by farms and villages. Many roads radiated outward from the fortress like spokes on a wheel. To celebrate the anniversary of his rise to power, the dictator ordered his generals to conduct a full-scale military parade. On the morning of the anniversary, the general's troops were gathered at the head of the roads leading to the fortress, ready to march. However, a lieutenant brought the general a disturbing report. The dictator was demanding that his parade had to be more impressive than any previous parade. He wanted his army to be seen and heard at the same time in every region of the country. Furthermore, the dictator was threatening that if the parade was not sufficiently impressive, he was going to strip the general of his medals and reduce him to the rank of private. But it seemed impossible to have a parade that could be seen throughout the entire country. The general knew, however, just what to do. He divided his armies up into small groups and dispatched each group to the head of a different road. When all was ready, he gave the signal and each group marched down a different road. Each group continued down its road to the fortress so that the entire army finally arrived together at the fortress at the same time. In this way, the general was able to have the parade seen and heard through the entire country at once, thus pleasing the dictator. All right, so we see now this is a different version of the fortress story with different surface features, but similar structural features. Here's another one. In a physics lab at a major university, a very expensive light bulb was being used in some experiments. One morning, the RA found that the light bulb was no longer working. She noticed that the filament had broken in two parts. The RA knew that the light bulb could be repaired if a brief, high-intensity laser beam could be used to fuse the two parts together. However, a high-intensity laser beam would also break the fragile glass surrounding the filament. What type of procedure might be used to fuse the filament with the laser and at the same time avoid breaking the glass? Since we've already gone through several versions of this story, my guess is that you can understand how those previous problems can be used to solve this analogous problem. Some of the classic research on analogic transfer use variations of all of these different problems that we have been talking about. So initially, the researchers found using the fortress as the source problem, the target as the radiation problem, there is a low level of surface similarity. So rays and soldiers don't have a lot of overlap conceptually, and then the fortress along with a tumor, those are actually also conceptually very different. So different surface similarity, but if you look at the structural similarity, the idea of breaking it apart and coming at it from different directions is very high. In terms of spontaneous transfer, only about 10% of people are going to use the source problem on the target problem to come up with a solution spontaneously. All right, so if participants get the radiation problem that they learned earlier with a solution, and then they get the target problem of the light bulb, that surface features actually are now a little bit more similar because we're talking about fragility, we're talking about damage, lasers and rays. I think there's a level of surface similarity that is greater for the radiation and light bulb problem compared to the fortress and the radiation problem. Structural similarity is very high. Plus, if participants know the solution and have been exposed to that, the surface similarity, the structural similarity are sufficiently high that people actually will spontaneously transfer. And then finally, the light bulb problem and the radiation problem, particularly if there is an emphasis on using a laser and the fragility of the glass, you get a high level of transfer spontaneously because of surface feature and structural feature similarity. So analogic transfer depends on whether people can apply a solution and more on whether they can recognize whether a past solution is relevant. Surface similarity drives retrieval, while structural similarity supports the correct application of the solution. So this table really illustrates that successful transfer depends more on structural similarity than on surface similarity. So people often miss that without cues. This led to this vast program of research by a researcher named Holyoake. Led him and a colleague to propose the multi-constraint theory. This is a theory about how people use analogies to reason and build arguments. So Holyoake and Thagard, I think. According to Holyoake and Thagard, people are constrained by three factors when they try to use or develop analogies. So structural consistency, semantic similarity, and purpose or goal alignment, sorry. So structural consistency, they suggested, was the most important constraint. Being able to map between the source and the target problem and preserve the relationship structure is really actually key for people successfully using analogies. One-to-one correspondence and higher order relations all need to line up. So, for example, multiple small forces converging have to map onto multiple low intensity rays converging. Number two, there has to be semantic similarity. So objects or elements in the source or target problems should be meaningfully similar. And this is where surface similarity really comes into play, right? So similar objects make retrieval easier and mapping smoother. The fortress to tumor is a harder mapping compared to the laser and radiation mapping. And then finally, you've got the purpose or goal of the alignment. So the source and target must have a similar overall goal and intent. So for example, destroying something, destroying a fortress versus destroying a tumor. The parade party is making something happen versus fixing the light filament. Like these are the kinds of things that feed into purpose or goal alignment. So from the analogic reasoning literature, there's a few conclusions that we can draw. So first, people rarely transfer solutions, they just learn. In the classic Glick and Holyoke studies, only about 10% of participants used a previous problem solution on a new problem spontaneously. So we're not very good at using analogies. That's kind of fascinating because we don't lack the knowledge. We lack the ability to retrieve and apply it. Like good solutions could be sitting in memory and we have no way to find it and have it influence our behavior. It also reveals the difference between surface and structural features, and people tend to align ideas based on surface features, even though it's the structural features that allow you for that analogic problem solving. It gives a mechanism for creativity. So many scientific discoveries have been identified through analogy, um, like protein structures, pasteurization. I want to say the double helix was like a balloon streamer. But essentially, it gives us a way to think about ideas and think creatively. But it also explains why teaching often fails. Students can understand something perfectly, but are still unable to use it later. What happens is that like abstract knowledge gets encoded along with the surface level details, and that literally makes the abstraction inert. So teaching really needs to help students abstract that schema by presenting multiple examples, and ideally in a table format so you can see the differences and compare them side by side. It's the side by side comparison that actually dramatically increases transfer, and that's one of the most practical insights in educational psychology. So lots of examples and side by side comparisons. A politician is trying to convince people to vote against independence in the Canadian province of Alberta. He says that voting for independence would be like leaving an ocean liner for a lifeboat without paddles on a stormy sea. This is part of the analogic paradox. Interestingly, people in psychology experiments tend to focus on surface features in analogy problems, whereas people in the real world frequently use deeper, more structural features. When we attempt to study analogic reasoning in a lab, garbage. But if you literally did an observational study where you went around and eavesdropped on conversations, you would hear people using analogies all the time and using them to great effect, which is the analogic paradox. We use them all the time, they're very useful, and yet we don't seem to do it naturally or on purpose. Here's where you can go do the H5P analogies. All right, let's talk about reasoning, starting with deductive reasoning. Deductive reasoning is like when you have a set of rules and you have to apply them accurately. So, deductive and inductive reasoning, we're starting with deductive reasoning. You are inferring a specific truth based on a general rule. So, conclusions should necessarily follow based on known principles. This contrasts with inductive reasoning, where you're looking at a specific set of examples and you're trying to infer a general rule from there. But we're going to start with deductive reasoning. And deductive reasoning is often discussed in the context of syllogisms. Syllogisms are forms of reasoning composed of two premises and one conclusion. And the idea here is that the conclusion has to logically follow based on the premises. You can think of the premises as like the rules. A syllogism is considered valid when its conclusions logically follow from its two premises. The best way to solve a syllogism is to actually like physically draw them out, map them out, like get out a piece of paper and try to like draw them in order to see whether or not they're true. And ideally, you're trying to falsify it. So here's a syllogism, two premises and a conclusion. We need to decide whether or not the conclusion is valid based on the premises. So all A are B, some B are C, therefore some A are C. Valid or invalid? It's always helpful to try to falsify the statement, and you won't, by the way, on the exam or on any assessments, need to solve syllogisms. We're looking at them for an example of a certain kind of reasoning. In philosophy classes, you will actually have to solve syllogisms. That's literally part of the training. But here we're looking at the cognition that goes into it. So try to falsify and draw it out. All A are B. That I've drawn that, so that's true. Some B are C, therefore some A are C. No, I can meet those two premises. Both of those two premises can be true without the conclusion also being true. So this is false. A is less than C. B is greater than C. Is B greater than A? To answer this question, most people report creating a timeline or either horizontally or vertically, and putting A, C, and B on a line relative to each other based on these descriptions. And this hints at something really important for deductive reasoning, which is mental models. You probably created a mental model to try to answer that question. And this is a mental construction of one possible version of that situation, and it's literally invoking mental imagery. Interestingly, research shows that people who lack mental imagery also struggle with deductive reasoning because we use mental models so much in these sorts of problems. So it turns out that spatial arrangements actually play a big role in mental models, and so they also play a big role in syllogisms. Syllogistic reasoning is correlated with spatial ability more than verbal ability, which I think is amazing because most of the time you think of philosophy as being a really sort of linguistic based logic, but in fact, we see a lot of spatial processing. People's ability to imagine a spatial arrangement or keep track of spatial arrangements really can strongly improve their ability to solve deductive reasoning problems. So by the way, spatial abilities would involve things like mental rotation, imagining shapes, and being able to mentally manipulate them, navigating based on sort of a bird's eye view map as opposed to using landmarks. So most people would put the elements ABC on a mental line using the premises and given the dictated the arrangement in order to answer this question. Interestingly, mental models generally exploit semantic meaning, or semantic information, so they're easier to form with more meaningful information, especially concrete elements that are easier to imagine. So the kitty is cuter than the iguana. The puppy is not as cute as the iguana. Is the kitten cuter than the puppy? Yes, right? Because we can picture all of that. Let's look at this craftsman experiment. Although the four craftsmen were brothers, they varied enormously in height. The electrician was the very tallest, and the plumber was shorter than him. The plumber was taller than the carpenter, who in turn was taller than the painter. It turns out that mental models are so important to deductive reasoning that there's evidence we pay more attention to the mental model than the information we use to base the model on. So, for example, asking the question, who's taller, the electrician or the painter, versus who is taller, the electrician or the plumber. The electrician and the plumber, their relative heights were literally explicitly mentioned in the same sentence, but because they're closer together in our mental model, we're slower to answer that question compared to the electrician versus the painter. Because in our mental model, those two people are further away from each other. Interestingly, brain damage to the right hemisphere, parietal lobe in particular, is most likely to interfere with participants' ability to use mental models and to solve sort of deductive reasoning problems. And people with right hemisphere damage also struggle with syllogisms, as you might expect. Let's look at an abstract problem for a second. This is what's called a conditional syllogism, so it's a selection task. You need to select which two cards to turn over in order to answer this question. Is it true that if there is a vowel on one side of the card, there is an even number on the other side of the card? Name the card or cards that you absolutely must see to correctly answer this question. Now, most people pick A, and yes, the answer is A because if there's no even number underneath, then the statement isn't true, right? We see a value, we should see an even number. But the most people then go on to say we should look under number 4 because if there's not a vowel on the other side, well, if there's not a vowel on the other side, the statement could still be true. You could still have, if there's a vowel on one side of the card, there's an even number on the other. It doesn't need to go in the other direction. It doesn't mean that if there's an even number on one side, there's definitely a vowel on the other side. It's only going in one direction, which means that you need to check under 7, because if there's no even number, there should also be no vowel. That's the real test. And this is abstract. Abstraction is tough. The falsification principle is when you actively look for evidence that would falsify the conclusion that you're trying to draw. If you encountered a kitty like this, you wouldn't assume that it had human legs, you would look for evidence that it didn't, right? You would actually look for evidence that this representation is false. We just don't tend to do that in logical situations on a regular basis. To test a rule, it's really actually necessary to look for situations that would falsify that rule. But we, most of the time, under formal logical conditions, do not take that approach. But what if we use a more concrete example? So here, is it true that if a person is drinking beer, she must be over the age of 19? This particular conditional syllogism is much easier for people to solve. Which ones do you check under? You want to check under A to make sure that if a person has beer, they're over 16. It doesn't matter. You know this, and you know this now concretely. It doesn't matter if the 22-year-old is also drinking a Coke. Like, they don't need to be drinking a beer. It's not like if you're over 18 or over 19, you have to drink beer. So then the other person, you want to make sure that the person drinking beer is over 19. You also want to check and see if the person who is 16 doesn't have a beer. So this actually suggests that there are two explanations for why concrete syllogisms are easier to solve. So one, they're concrete. It's easier to form mental models of concrete rather than abstract problems. But then number 2, which in this case probably explains more of it, is that it's called the pragmatic reasoning schema. It's a way of thinking about cause and effect in the world that's learned as a part of experiencing everyday life. We know the laws of the land. We know who should be allowed to drink alcohol and who should not. And the idea here is that it's just easier for us to apply that because of that prior experience. This suggests that if we switch the statement, people would struggle with confirming it. So if a person is drinking beer, she must be under the age of 19. You would need to check under beer, and then you'd need to check to make sure that the 22-year-old is not drinking alcohol. This actually tremendously diminishes people's performance. So when you flip it so that it's the opposite of what you experience in daily life, it's much harder to apply it. Okay, here is where you can go do some practice on deductive reasoning. Maybe I should grab something to drink. Inductive reasoning. Inductive reasoning is the opposite of deductive reasoning. Shocker. So with deductive reasoning, you're having these specific rules that you are applying to specific cases. In inductive reasoning, you're having these specific cases and you're trying to infer what the general rule is. And so with inductive reasoning, you could be wrong. You can suggest a conclusion with varying degrees of certainty, but your conclusions do not necessarily follow from the premises. You end up judging how likely something will happen based on observations about what's happened in the past. Here's an everyday example. It's been raining all week. Will it rain tomorrow? So this is inductive reasoning. Are you certain it's going to rain tomorrow? No, but like if it's been raining all week and it's Vancouver, then probably it's going to rain tomorrow. And you can't actually be sure. You're drawing a probable conclusion from patterns or evidence, but the conclusions are uncertain but useful, right? Like if you are trying to figure out what to do tomorrow and you are not sure how the weather is going to be, but it's been bad all week, probably it's going to be bad again tomorrow. And so you're contrasting this with deduction. With induction, you've got probability. With deduction, you have certainty. So obviously inductive reasoning is the more interesting form. Okay, so here's some real world examples. Coffee. You might start to recognize a pattern, or you might identify what you think is a pattern that drinking coffee after 12 p.m. interferes with your ability to sleep. That might or might not be wrong. Social judgments, first impressions. You're making inferences about the kind of person that you're meeting based on first impressions, and like that could be wrong. Scientific reasoning. You start with a bunch of data in order to try to infer a more general theory, which could be wrong. So inductive reasoning matters because it's really core to our ability to make predictions about the world, which next week we will talk about a lot. It's how we make decisions under conditions of uncertainty. It's how we learn from experience. Most real world cognition is inductive in nature. The Wisconsin card sorting task is an example of inductive reasoning in action, and I include a link to a demo in the activity for you guys to try out, which is like honestly meditative. I tested it just to make sure it was working, and I probably played it for probably like 10 minutes, and you know it doesn't need more than 30 seconds of testing, but it's relaxing. So what happens with the Wisconsin card sorting task is you have these 4 piles and you're given a card and you have to decide how you're sorting it. So you could put it in the first pile, which means you're sorting based on the number of items on the screen or on the card. You could put it under the second pile, which means you're sorting it based on color. You could put it on the 4th pile, which means you're sorting it based on shape. But you can see like there's a bunch of different rules here. And the thing about the Wisconsin card sorting task is people are not told the rule. They get a card, choose which pile to place it on, and then they get feedback. Did you get it right or did you get it wrong? If you got it wrong, then you have to try again. Once you figure out the rule and get like X number of trials correct, usually what happens is the rule will change and you measure how long it takes a participant to identify that the rule has changed and figure out what the new rule is. Okay, so more interesting than inductive logic and examples of it are the errors of inductive logic. People often fail to consider a comparison group, or they fail to consider the base rates of a specific example or a specific event. So for example, more graduate students are firstborn than secondborn. The general rule that people often infer from this data is that firstborn must be smarter than secondborn. But some people only have one kid. And so there's just more firstborn people in the world compared to secondborn people. So ignoring base rates is kind of a problem. Here's another example. Ted is attending a professional conference comprised primarily of physicians, 80%, and a small proportion of legal practitioners, 20%. He demonstrates a low tolerance for presenters who exceed their allotted speaking time, which he characterizes, often quite publicly, as clear violation of the schedule. During a conference lunch, he assumes control of the conversation, detailing the scope and success of his practice, including references to his billing and related performance metrics. By the conclusion of the meal, several attendees have discreetly excused themselves, while Ted appears unaware that his conduct has alienated most of those at the table. Is Ted more likely to be a doctor or a lawyer? In trying to judge whether Ted is likely to be a doctor or a lawyer, people tend to rely more on the descriptions and how consistent those descriptions are with their concepts of a lawyer and how less consistent they are with their conceptions of a doctor, instead of paying attention to the base rates. 80% of the participants are physicians. The likelihood that Ted is a lawyer is already very low. And could these descriptions apply to a doctor as much as a lawyer? Like, yeah, they probably could, especially at the individual level. So ignoring base rates. Always pay attention to base rates. Confirmation bias is also a problem. So confirmation bias is a tendency to seek information that confirms your beliefs, or it's the disinclination to seek evidence that would indicate whether a hypothesis is false. The reason why I have this image up here is because traditionally the red elephant has been used to it's like a symbol of the Republican Party, and the blue donkey is a symbol of the Democrats. And obviously we know way too much about American politics, but that I thought was a good example of confirmation bias, because I see it all the time. People in either camp selectively looking for evidence that that confirms their own beliefs. People are just much more likely to try to confirm their beliefs than they are to look for evidence that might falsify what they think. So, for example, if you have the sequence 2, 4, 8 and ask a person, what's the rule? You get to test your hypothesis before you explicitly state the rule, but first you have to guess and find out if you're correct. And what people tend to do is identify their rule and then test it in ways that try to confirm that their answer is correct, as opposed to trying to look for evidence that their solution is not correct.
I'm going to give you guys 3 numbers, a 3-number sequence, and I have a rule in mind that these 3 numbers obey. And I want you to try to figure out what that rule is. But the way that you can get information is by proposing your own set of 3 numbers, to which I will say, yes, that follows my rule, or no, it doesn't follow my rule, and then you can propose what you think the rule is. Is that fair?
Yeah.
Yeah, okay, so here are the 3 numbers. 2, 4, 8.
2, 4, 8.
You don't need to continue the sequence, you can propose a totally different sequence, whatever you want to propose, and I will simply say yes or no, that follows my rule.
2, 4, 8. 16, 32.
16, 32, and
64.
those also follow my rule.
Okay.
What's the rule? What are you thinking?
Multiply by 2.
That is not my rule.
What?
That's not my rule. But you're allowed, if you want, propose 3 other numbers.
3, 6, 12.
3, 6, 12.
3, 6, 12 follows my rule.
10, 20, 40.
10, 20, 40.
That follows the rule.
Yeah, I'm still multiplying by 2.
I know. I know what you're doing. And yes, it follows my rule, but no, it's not my rule.
5, 10,
10 and 20.
Follows my rule.
100,
200, 400.
Follows my rule.
500, 1,000, 2,000.
Follows my rule.
Want me to keep going?
But do I just keep going? You're going to tell me your rule?
Am I doing it the wrong way? Am I approaching this the wrong way?
You're totally fine,
Okay.
but you're approaching it the way most people approach it. Like, think strategically about this. You want information.
Yeah.
I have information. The point of the 3 numbers, right, is to allow you to figure out what the rule is.
Okay.
Okay, I'm going to give you the numbers that I don't think fits the sequence and then see what you say. So I'll say 2, 4, 7.
Fits my rule.
So whatever I propose is right?
So is your rule like you can propose any number?
So the rule is anything we say is yes.
No.
Damn it.
But you are on the right track now. Hit me with 3 numbers.
3, 6, 9.
Follows my rule.
Oh, that didn't follow my rule.
This is good, right?
5, 10, 15.
That follows my rule.
What? Oh. Really?
Yeah.
I don't believe this.
1, 2, 3.
1, 2, 3.
Follows the rule.
What about 7, 8, 9?
Follows. Yes, that follows the rule.
8, 16, 39.
Fits the rule.
Excellent.
But we're no closer to the rule. I want you to get to the rule. How about 1, 7, 13? Follows the rule.
What?
11, 12, 13.
How does this
Follows
make
the rule.
sense?
10,
I don't
9,
know how
8.
to do this.
Does not follow the rule.
10, 9, 8 does not.
Oh, so is it all in ascending order?
Booyah.
Okay.
Up top. Yes, first
that
ones
what
to
it
get
is?
it. You guys nailed it. That's the rule. That's
so
the rule. Increase numbers in increasing order.
Aw.
Numbers in ascending order.
Oh, so much
1, 2, 3, 4, 5, 6, 10, 15, 25. Doesn't matter. Any numbers in ascending order. I was inspired to make this video by the book The Black Swan by Nassim Taleb. Now, the black swan is a metaphor for the unknown and the unexpected. I mean, in the old world, the theory was that all swans were white. So each instance of a white swan would make you think, yeah, that theory's pretty good. But the point is, you can never prove a theory true. And in fact, when people found Australia, they realized that there were black swans. What was interesting for me was that everyone I spoke to came up with a rule very early on and then only proposed numbers that fit with that rule they were thinking. I was looking for you guys to propose a set of numbers that didn't follow your rule and didn't follow my rule. I was looking for you guys not to try to confirm what you believe. You're always asking something where you expect the answer to be yes, right? Like you're trying to get at it.
But instead you want to get the no.
You want to get the no because that's much more informational for you than the yes. Like if everything's
No, that
giving a
is
yes.
true. That is really true once you say that.
That is what's so important about the scientific method. We set out to disprove our theories. And it's when we can't disprove them that we say, this must be getting at something really true about our reality. So I think we should do that in all aspects of our lives. If you think that something is true, you should try as hard as you can to disprove it. Only then can you really get at the truth and not fool yourself.
Love it. This guy is a content producer who kind of focuses on science and obviously from BC. I don't think that he's in Vancouver anymore, but a lot of his early work you can clearly see he's in Vancouver. So just shout out to a local content producer who does good work. Okay, so confirmation bias actually can be a bit of a problem for deductive reasoning too. Going back to the example where vowels and even numbers should be matched up, people typically pick A to confirm that there's an even number on the other side and 4 to confirm that there's a vowel on that other side. But really, they should be trying to disprove that statement to test it. That really is what puts it to the test. And in the real world, it's very difficult to prove something is true, as that video really highlights. It's much easier to look for false evidence. So, for example, if you take this statement, all dogs are brown, you could spend your whole life collecting examples of brown dogs, but all you need is one example of a white dog in order to disprove this statement. So, falsification is always much more effective than trying to confirm. So within the problem solving space, there is this distinction between algorithms and heuristics. This is an example of an algorithm. Yes! 5.6 seconds, that's impressive. I think most people these days know that solving a Rubik's Cube comes down to following a set of steps. So the algorithm, and it follows an algorithm. And an algorithm is a procedure consisting of a series of steps that will solve a specific type of problem. Rubik's Cube has an algorithm. The solution guide is very specific. It's also pages long. But if you want to learn it, the algorithm is out there for people to learn. This is when you're seeing people do those like super fast solutions. It's not because they are really good at solving a Rubik's Cube. They're really good at implementing this algorithm. So an algorithm is a procedure consisting of a series of steps that will solve a specific type of problem if you follow it correctly. But most of the time, we do not have an algorithm, or a lot of times algorithmic problem solving is very clunky. It takes a lot of time and effort. Heuristics are rules of thumb that guide us. They're not guaranteed to solve a problem, but they're often much quicker than using an algorithm. And this is where we use past experience to help guide present behavior. We're judging like how likely something is based on our observations about what has happened in the past. For this reason, heuristic reasoning falls under the domain of inductive reasoning. One of the primary examples of heuristics, cognitive heuristics, is the availability heuristic, which states that events that are more easily remembered are judged as being more probable than events that are less easily remembered. For example, people tend to judge the numbers of words that start with R as being greater than the number of words that have R as the third letter. But that's in large part because it's way easier for us to think of words that start with R compared to words that have R as the third letter. I think one of my favorite examples of this, I think it's just like, it's perfect. It's a perfect little experiment. Researchers had participants learn lists of names that were composed of famous and non-famous names of men and women. And the way that they manipulated it, there was always 12 famous names and 14 non-famous names. In the first version of the experiment, all of the men were famous and all of the women were non-famous names. And what the researchers found was that participants, when asked if there were more men or women on the list, people estimated that there were more men on the list compared to women because they could recall those names. But this is not about people remembering men's names better than women's names, because they replicated this where they literally switched it and they found the same thing, that people were just estimating that there were more famous people on the list compared to non-famous people because those names are easier to remember. And availability has also been linked, the availability heuristic has also been linked to illusory correlations. Correlations appear to exist, and sorry, this is where correlations appear to exist when they really don't, or the correlation is actually much weaker than people think it is. So correlations are not intuitive. Generally, people need to be formally instructed on correlations in order to calculate and recognize them effectively. But in this experiment, researchers presented these probabilities of symptoms versus disease. And because looking at this, you can see that in terms of the highest number here, we see that participants or these imaginary patients who have the disease and symptoms present, the highest number is 37. And so when presented with this data, nurses generally inferred that there was a connection between having the symptoms and having the disease, when in fact, if we look at the total proportion, both patients who had and didn't have the disease had about a 70% likelihood of symptoms being present versus absent. So there was no relationship, but the largest number of cases occurred in that cell labeled symptom present and having the disease. And so what happens is people tend to focus on instances that are consistent with the hypothesis that the disease and the symptoms are correlated. It's an example of confirmation bias for sure, but also availability heuristic and probably the representative heuristic as well. So let's look at an example. Natalia is a warm and eccentric woman with an undying love for cats. Her cozy apartment is decorated with feline-themed art, shelves lined with cat figurines, and plush cushions embroidered with tiny paw prints. She shares her home with 3 beloved rescue cats, Mochi, Whiskers, and Luna, each with their own distinct personality. Natalia runs a small online shop selling handmade cat-themed accessories from enameled pins to knit cat ear beanies. She volunteers at a local animal shelter on weekends, helps socialize shy kittens, and her social media is a constant stream of adorable cat photos, fun facts, and memes. If there's a cat cafe in town, you can bet Natalia's already been there probably twice. Is Natalia more likely to have a blog or more likely to have a blog about cats? After reading this description of Natalia, more people than not suggest that Natalia is more likely to have a blog about cats than to just have a blog. And this is the conjunction fallacy. The conjunction rule is that the probability of a conjunction cannot exceed the probability of its constituents. People who blog about cats are always going to be a subset of people who blog. That's the conjunction rule. That just literally has to be the case. But what we see is that based on the representativeness heuristic, people basically ignore the conjunction rule and engage in the conjunction fallacy. So Julia is a student. Is it more likely that Julia has a backpack or that Julia has a backpack and hangs out at the library? Again, people who have backpacks and hang out at the library are a subset of people who have backpacks. It's definitely going to be a smaller proportion. But the conjunction of backpack plus hanging out at the library is more representative of what a student is likely to, of the behaviors a student is likely to exhibit. And so people commit this conjunction fallacy, that judgments under uncertainty are often mediated by intuitive heuristics that are not bound by the conjunction rule. And in fact, people suggest that the conjunction is more representative and endorse that. The representativeness heuristic implies that people believe a given category exemplar ought to resemble the category prototype. So for example, TED and at the conference, we're judging the subjective probability of an event based on the extent to which that event resembles or is representative of the salient features of its parent population. So this is an example of ignoring base rates, but it's because of the representativeness heuristic that happens. Okay, here is where you are off to go do the inductive reasoning and heuristics, H5P. Okay. All right, it's the end of the lecture. You should be able to Explain the relationship between Gestalt psychology and insight problems. Describe the evidence that insight is not epiphenomenal. Summarize Wallace's 4 stages of moments of illumination. Describe incubation and the evidence that it's helpful for insight problem solving. Summarize the explanations for why incubation is helpful. Explain fixation and contrast it with functional fixedness. Use evidence that children under 6 aren't subject to functional fixedness. Describe mental sets. Explain design fixation and predict how similar situations might bear out. Explain analogic transfer. Describe the effects of a source problem on solving a target problem. Summarize the multi-constraint theory. Contrast surface and structural features. Explain the analogical paradox. Recognize examples of deductive reasoning. Explain how mental models are used in deductive reasoning and the effects of that result. Contrast performance on abstract and concrete deductive reasoning and the effect of that difference. Recognize novel examples of inductive reasoning. Describe some of the common logical errors in reasoning. Explain and use the falsification principle. Compare and contrast heuristics versus algorithms. Identify novel examples of the availability heuristic and representativeness heuristic, and explain how the availability heuristic and representativeness heuristic contribute to the conjunction fallacy and illusory correlations. And we are done. One more to go, my friends. Hang in there.